Hydrogen NMR and carbon-13 NMR and infrared spectroscopy are used to distinguish between compounds and identify them. Give the skeletal form of the compound that's used as standard when recording 13 carbon NMR. It's something called tetramethylsilane. It's a silicon atom surrounded by 4 methyl groups. The skeletal formula will therefore look like this, because the methyl groups are ends of lines or corners of lines without the hydrogen showing. 4 isomers, P, Q, R and S. The carbon-13 spectra are shown on the next page. The first one has 4 peaks, the second one has 4 peaks, and the bottom one has 5 peaks. So let's have a look how many peaks they produce, how many different carbons there are. Well, this is off center, so it's not symmetrical. So that's carbon in one environment, a CH3 joined to a CO, 1, 2, and then that CH2 is joined to a CO, 3, CH2 joined in the middle, 4, CH2 joined to a CH3, 5, 6. That's got 6 different ones. So P doesn't feature at all. None of those are P. There are no 6 peaks. So we're looking between Q, R and S. Q has these two CH3s here are the same, so that's 1, 2, 3, 4, 5. Q has 5 different peaks. And R, those 3 methyl groups are all the same, so that's 1 carbon environment producing 1 peak, 2, 3, 4, and this one, 1 for each of the methyl groups, 1, 2, 3, 4 as well. So R and S have 4 and Q have 5. So the 5 is Q. There's nothing with 6 peaks, so P doesn't feature. Now we've got to decide between R and S. So between R and S, the only thing I notice is that Q here has a peak with 2 peaks very close together, which is very similar to this one. This one looks fairly similar to Q. That one's offset and it's got an extra peak. But this peak here, this double peak here, very close, seems very close to Q. I'm going to look for something between R and S that's similar to Q. Something between R and S that's similar to Q. I think the one that's most similar to Q is R. So I'm going to go with R as this one and this one as S. Identify from the infrared spectra, we've got C6H12O2 and I've got to find out what's in each. Well, they've all got a CH, so CH is at 3000, so this peak here is 3000, that's the CH, and the CH here is hidden by a broader peak here. This one's an OH, so it's got an OH, a broad peak at around about 3500, and this one has got an OH as well, a rather broad peak at around about 3000. So this one has got an OH here, it's got a CH here, and it's got a C double bond O here at about 1500, 1600, maybe 1700. It's got a CO, so it's got an OH here at 3500, a CO here, but it hasn't got a signal at 2500 to 3000. It's got nothing in this region, so it's not a carboxylic acid. It's got an OH and a CO. Remember, we're looking to try and identify the 2 O's. So in T, there's an OH and a CO. That then covers both O's. That means both O's are taken care of. The U has a peak OH here. That's a broad peak. Then it's got CH here at 3000. It's got nothing else apart from the fingerprint region. So it's only got an OH, but it's got 2 O's, so it must have 2 OH groups. And V, finally, what's V? V 3000, big broad peak, is an OH. It's got an OH in there, and it's got a CO in there. And this broad peak here is also showing a carboxylic acid group. Probably a carboxylic acid group has a signal at 2500 to 3000, somewhere around here. It has got one, not like this one that's missing it. It's got a very broad peak here. I think that's a carboxylic acid.